Okay, so good morning, everyone. This is the lecture six for uh, for the radiation topic, and today we are going to discuss about background radiation. Okay. Now, in the previous class, also we talked about some of the naturally occurring radiation, and I also mentioned that we or like everything on the Earth, they are exposed to radiation, right? So basically, we are always exposed to the background radiations. So some radiation are always falling on us. Um, so background radiation is all around us, and the average annual background radiation in the UK that most of us experience or are exposed to is around 2.2 millisieverts, right? So this SV is your sieverts. So millisieverts. It's quite a small quantity and it's not harmful enough for us. But just to give you an idea that all of us, we are always exposed to radiations, right? And those radiations, they are called as your background radiations. Now, where do they come from? Right? So some of it comes from natural sources and some comes from artificial sources. So basically for these radiation or the background radiations, you have some natural sources which are radioactive and produces radiation, and some of them are artificial sources. That is because of man-made activities, right? So because of that, we also produce some amount of radiation, or basically we also contribute into this background radiation. Uh, Humans have always been exposed to continual background of radiation. Now, I don't know if you noticed in the experimental demonstration for the Geiger-Müller experiment, if you noticed that you had the Geiger-Müller tube, and in that experiment, what the person was doing is he was bringing the different types of radioactive material in front of it, and this Geiger-Müller tube was connected to a counter and a speaker. Yeah. So when these radioactive materials they were brought closer to the Geiger-Müller tube, the the speaker was making a popping sound, and as and when if you bring it closer, the popping sound would increase. But along with that observation, if you would have noticed that when there was no radioactive material, even then the speaker was making some popping sound, right? That means there were some radiations which were entering this Geiger-Müller tube. So there is some background radiation present all around us. Yeah. So background radiations can be divided into two groups according to the source, naturally occurring radiations and artificially or man-made sources. So some of the examples of your natural source of background radiation is your cosmic rays, right? So these are the rays which are reaching the Earth from outer space, right? So sun also it produces some kind of radiations, um, and there are several celestial bodies which also generate radiation, and they can propagate to the Earth, and those are your cosmic rays in form of radiations to fall on us. Then, along with that, there are certain rocks and soil which are radioactive or they produce radiation. So one of the very common type of rock is your granite, right? So granite, they they are radioactive, and produce radiations. I think those playing marbles, if you see, they are made out of granite. And if you place them in front of this Gigamuller tube, you could see an increase in the count or the popping sound, or the speed of the frequency of popping sound would increase. Right. Now, since these radioactive materials, they are present in the soil, so the plants, or the living things, what they do is they absorb these radioactive material from the soil and they pass it on into the food chain, right? So if your soil is radioactive, the plants will, absorb those radioactive materials, and when the cattle, they would eat it, then that radioactive, you know, will be passed on into the food chain. So for most people, natural sources contribute the most of their background radiation dose. So most of us who are not working in the radioactive environment, generally, this is the we are generally exposed to only 2.2 millisieverts of radiation throughout our life. Right? So we'll discussed about this absorbed dose in the later classes. We'll take up some questions based on this as well. But absorbed doses is measured in sieverts. So the amount of radioactive activity absorbed by something is measured in sieverts. Let's talk a little bit more about the cosmic rays. So these cosmic rays, they are high energy particles, right, which are coming from the outer space or from the sun. So primarily, these cosmic rays, which are mostly photon, they lose energy by colliding in the atmosphere and produces secondary cosmic rays such as gamma rays, electrons, and neutrons. So we all know that our Earth is surrounded by kilometers of atmosphere, right? So above the Earth's surface, we have the atmosphere. So these cosmic rays, which are high energy particles, what they do is they collide with the atoms which are present in the atmosphere, and then these are due to this collision, these atoms would produce some secondary radioactive radiations, or alpha, beta, or gamma rays. And those are the radiation which falls on the Earth, right? So it's generally not the cosmic rays which is directly reaching the Earth's surface, but most of the radiation is because of the secondary radiation produced by the cosmic rays. So kind of like these cosmic rays, they, uh, you know, amplify, or they get amplified because of these secondary radiations. And obviously, because of this atmosphere, we could say that if we go to higher altitudes, we would be exposed to more amount of radiation. So generally, we could add 0.01 millisieverts of radiation as our absorbed dose, as and when we go or rise 30 meters above the sea level, right? So as and when we are going to higher altitudes, we could add 0.01 millisieverts for every 30 meters, we go above the sea level. So people in Denver, they would receive approximately 0.9 millisieverts per year in cosmic radiations, right? So they would receive a higher dose of radiation in comparison to people living on or near the sea level or at a lower altitude. And even when we are taking a flight, a transatlantic flight, generally we would be exposed to 0.5 millisieverts of radiations. So during the flight, we would absorb approximately this amount of radiation because of this background radiations, right? So basically, the moral of the story is as and when we climb or go to a higher altitude, we are exposed to more amount of background radiations, right? And since granite is a natural source of radioactivity, these granite, they would produce radiation. So people living near the granite structures or basically the granite mountains, uh, they would be exposed to about 5 times the average equivalent dose, right? So they would be exposed to 5 times more of background radiation in comparison to those people who are, living in some different regions. Rocks and soils, they contain traces of radioactive material. So mainly this uranium and thorium. These are your minerals, which are or basically radioactive materials which are present in rocks and soils. And then you can refine them and use it as a nuclear fuel in some kind of like for producing electricity nuclear in the nuclear power plants. Um, so basically, after refining, you could get radium, potassium. So those are your derivatives of uranium and thorium. So uranium and thorium, they are again naturally occurring radioactive materials, which can be transformed into different chemical compositions by refining them, and they could be made more radioactive and can be used for in the power plants. Yeah, so granite is more radioactive than brick or sand, and areas where there are a large number of granite have higher background rates. Example, Aberdeen and Dartmoor. Right, so these areas, if you take a Gigamuller tube and measure the radiation, you would find a slightly higher rate of background radiation in these areas. Right? So obviously, because Aberdeen is quite elevated, it's at a higher altitude, and along with that, there are some granite deposits in that area, so that further increases the background radiation in those areas. Okay. Now, there is a little we know about the natural background radiations. So since there are several, so many different types of background radiation or naturally occurring background radiations, which are coming from all together different type of sources. So although we could identify some of the sources, but still we are quite unaware about all the sources, naturally occurring sources, which are responsible for the background radiation. There are certain, artificial sources or basically man-made or because of human activities. So because of human activities, we also contribute into this background radiation. So some of these activities are your nuclear power stations, right? radioactive fallouts from the nuclear weapon testing, right? And medical X-rays. So even the X-rays, they would also get attenuated, and again, they would be acting like a radiation, right? So they would contribute into the background radiation sources, right? So these artificial sources are also responsible for contributing into the background radiations. Right. So having talked about uh, the different types of background sources of radiation, both artificial and natural sources, let's now talk about different methods or different equipments which we can use to measure these background radiations, or in general, we can measure radiations. So this one, Geiger-Müller tube, we have already seen one, and we have seen how they measure the background radiations. So we can detect radioactivity with Geiger-Müller tube. Right? And inside the tube, there is a gas. So usually they fill this Geiger-Müller tube with some kind of gas, usually it's argon, right? And when radioactive activity they enters the tube through a thin window made of mica in front uh, of in front of this tube, or from the walls of this Geiger-Müller tube. Um, what happens is that they would ionize the gas which is filled in this tube, right? And as a result, what would happen? So when these radiation they would fall on these atoms, they would knock off some electrons from the atoms in the surrounding medium, right? And as a result, these atoms of the medium they would get ionized. Right? Now these electrons, along with this tube, what it has, this Geiger-Müller tube has is an anode, right? So right in the center, you have a metal copper wire, which is connected to the positive terminal. And the outside chamber, or basically the tube itself, it is connected to a negative terminal, right? So the outside tube is negatively charged, and the rod or the copper wire in the center, it is uh, positively charged, right? So when these radiation, they enter into the tube, either from the mica window or from the sides, what they would do is they would generate electrons, right? Basically, they would ionize, they would knock off some electrons from the atom, and those electrons, they would get attracted towards the anode, right? So those electrons, they are negatively charged, and since the metal wire in the center, it is positively charged, so they would get attracted towards the positively charged wire. And over a period of time, although it's quite short, but the electrons will get deposited on this anode, right? And a significant amount of current, right? So current is the flow of electrons. So these electrons, after getting attracted towards the anode, they would start flowing in this wire. And if you connect a speaker or a counter in the circuit, right, you would hear some popping sound, or you would see an increase in the count. So that's how your Geiger-Müller tube it works. So it works basically on the ionization of the atoms. So So here in the animation, you could see that some of the electrons, they are, getting generated and because of ionization and getting attracted to the wire in the center. And when sufficient amount of electrons, they are collected, they would start flowing in the circuit. And if you connect a counter or a speaker, you could see an increase in the count, or you could hear some popping sound. Now, what I would like to do is to have a little bit discussion about the advantages and the drawback of this Hieger-Muller tube. So, I would like you all to tell me some of the advantages. I will pause the recording now. So, in the discussion, we found certain advantages and certain disadvantages of Hieger-Muller tube. We realized that this Hieger-Muller tube, it has the advantages such as it could measure all the three types of radiation, and it's quite sensitive because it could measure even a very small amount of background radiations. However, this Hieger-Muller tube, it has certain disadvantages, such as like it cannot distinguish between whether it's a alpha radiation or a beta or a gamma radiations. Right? It's not very selective, we could say. And then this second disadvantage is that it is not very portable, right? So for people who are working in radioactive environment, or maybe some of the people who are working in nuclear power plant, if they have to carry that entire setup along with them all the time, it would be really, tiresome for them. So for such type of applications where you are mainly concerned with how much of radiation you absorbed on a particular day, or whether you are only concerned whether the environment in which you are working is radioactive or not. In such type of situation, or for such applications, we could use this film badge, right? So people working with radioactive material, they often wear a badge containing photographic film, right? And that's called your film badge. So photographic film, it's the same photographic film which we use to print the photographs. So nowadays, most of us, we use digital cameras, but in the older cameras where you have a reel of these photographic films, right? So these photographic films, usually they are gray in color, light gray, right? And when they are exposed to light or any kind of radiation, they would turn dark, right? So if they are exposed to some kind of radiation, maybe at this point, so this region, this small region would turn dark, right? So these photographic plates, what they have is they are basically coated with silver bromide crystals. Right? So on this photographic plate, you have a coating of silver bromide. And when they are exposed to some kind of radiation or light, they turn dark. Otherwise, naturally their color is light gray. Naturally, the photographic plates, they are light gray in color, but when they are exposed to radiations or even light, uh, they would turn darker. So in this film batch, what they have is they put a photographic film in a light proof cover, right? So basically it's covered from all sides and there is no light entering this batch, right? And what happens is that you have two types of filter over here. The first one is you do not have any kind of filter or any material over it. It's simply covered in plastic. Mm, In the second part of this photographic or second part of this photographic plate, or the middle part of this photographic plate, is covered with aluminium, right? So there is an aluminium sheet covering the second half or the middle section of this photographic plate. And the bottom section of this photographic plate, it has a lead filter over it. So basically it has a thick layer of lead which is placed above the photographic plate, right? So what would happen usually, I mean, this film badge is only used for measuring beta and gamma radiations, although it could measure alpha. Um, Not really. It won't be able to measure alpha. It can only be used to measure beta and gamma radiations. Right. That's a question for you in the tutorial section. Right. So this film badges, they could measure only beta and gamma radiations. Um, so when both this beta and gamma radiations are present in the environment, what would happen is the top section, right? So top, middle, and bottom. Right? So the top section of the film would turn darker, right? Because it both beta and gamma radiation will be able to pass through. Uh, the middle section of the photographic film would again turn dark because although this aluminium filter can stop the beta radiations, but still your gamma radiation would be able to pass through. Right. So again, the film will be exposed and it would turn a little darker. However, the bottom section of the photographic film, it would be light gray. I could not find a lighter shade of gray while making this figure, but it's generally lighter than the color which I have, or the shade which I have shown here. Right, so the bottom section would remain to be light gray. Okay, and if you are exposed to only beta radiations, in that case, the top section uh, of the photographic film will turn darker because both beta and gamma radiations could pass through. So the top section would turn darker, whereas the middle and the bottom sections of the photographic plate, it won't. It would remain, light gray because you have aluminium filter over here, which would stop the beta radiations, and then you have lead, which could again stop the beta radiations from exposing that film. Right. So based on this type of color changes, after the shift, what the workers, what they do is after their shift, after they complete their work, what they do is they submit this film badge, and in the labs they would develop the film, and based on this type of shade difference, they would identify whether you are exposed to alpha, beta, or both alpha and beta radiations, right? Sorry, not alpha, beta and gamma radiations, or either of them. Right? So based on this type of shade difference, you could identify which type of radiations you are exposed to, and at all if you are exposed to a radiation or not. So during my internship for my bachelor's degree, I happened to visit uh, cyclotron center. So it was a research center, and they used to work on these kind of like nuclear fission and fusion. So I happened to visit the cyclotron I saw the cyclotron. It was nothing interesting because the entire setup, it was all around covered with lead, a thick layer of lead, and then there were concrete walls around it. So we could only see it through a very small, I think, glass window or something. And it was simply a concrete structure in front of us. So that was nothing fancy. But then before entering that facility, although it was not operational at time, so there were maintenance going on. So we were also given with this kind of a badge. Um, like for me, they did not wrote down my particulars. Rather, for visitors and for interns, they had a serial number written over it, and they simply asked us to enter our name and contact numbers in a diary, and they note down the serial number of the badge they were issuing us. And I didn't receive any call after that. So hopefully I was not exposed to any kind of radiations. And also, there were maintenance going on, so it was not operational. So hopefully, there was no radiations around there. Right. So yeah. So nowadays, even like digital uh, badges are being used. So this type of film badges, they are not quite popular nowadays. Um, they have been replaced with the digital ones. Now I will pause the recording and let's again discuss a little at some of the advantages and disadvantages of this type of detector. Okay, so we discussed some of the advantages and disadvantages right now. So one of the obvious advantage is it is quite portable, right? It could be easily carried. Some of the disadvantages are it could not distinguish between the energy of radiation, how intense that radiation is, right? Uh, Although it could detect beta and gamma radiations, but it could not detect the intensity of the radiations. Another disadvantage is detection time is quite long, right? So after your shift or after the worker, they have completed their shift, they would submit it to the lab. The lab person will, the technician would develop the film and then tell him that yes, you were exposed or no, you were not exposed to radiations, right? So that entire process is quite time taking. It's not real time analysis of radiation, right? Another disadvantage is that it could be quite sensitive to the environmental interference, such as heat and all, right? So because of such situations, even your film could be exposed and you could observe some dark patches over there. So we have another type of detector. That's called your spark counter. So we all know, so spark counter, they are suitable for measuring alpha particles, alpha radiations only. Alpha particle radiations. Now, we know that alpha particles, they have the highest ionizing ability. Right. So in this type of spark counter, what they have is they have a high voltage source uh, and they have a mesh over here. Right. So this copper plate in the center, if you could see that um, there is a cavity over there. Right. So that cavity, in that cavity, you have a mesh, right? A metal wired mesh. So that is connected to one of the, either the positive or the negative terminal. Usually it's connected to the negative terminal of the high voltage source. And then although it's not visible. So you have a mesh over there, and just below it you have a wire, right? A copper wire, which is, so this mesh is connected to the negative terminal, and the wire, the copper wire, conducting wire, it is connected to the positive terminal of the high voltage source. And what we do is we, um, you know, this height or the is the height of the plate you could adjust, right? So you have a wire and a plate over it. So you could adjust the distance between them. And what we do is we increase the amount of voltage, and until unless there is a spark being generated, right? And what we do is we adjust uh, the voltage. We So what we do is we fixed the height, and then we increase the voltage so that there is a continuous spark, and then we reduce it just to a value when the sparking stops, right? Now, when a radioactive, or basically a radioactive material which is emitting your alpha particle, is brought near this type of spark counter, what happens is that it would ionize the medium, right, between the mesh and the conductor. As a result, your medium will become conductive and you could observe some sparking. Right. So I have a video, a 2-minute experimental demonstration for this, which I will share with you. You could see this experiment demonstration, and we will continue after that. Okay, so it's a 2-minute video, and let's take 3 minutes for that. Okay. That should be. Right, so we quickly had a discussion about the advantage and disadvantage. So we would like to keep it in the middle, between advantage and disadvantage, that the spark counter is able to detect only alpha particle or alpha particle radiations, right? Um, in a way, it is a disadvantage because it's unable to detect the other type of radiation. But again, it is, in a way, it's quite selective because it's able to detect one particular specific type of radiation, right? That is your alpha radiation. And since it has the highest ionizing ability, so it is most harmful for any living being, right? So it's quite important to detect alpha particle, and we have a detector for it. Now the last one is your scintillation counter. So scintillation counter, basically scintillation is the property of a material that when a charged particle enters, it absorbs that energy and leads to the emission of light. Right? So whenever these charged particles or these radiation would enter into this yellow block, or that's your scintillator, right? It would get absorbed by that medium and produce a light energy, right? So scintillation counters, they rely on fluorescent nature of some substances, right? So we might have seen some fluorescent material, right? So when even in the night or in the dark, they would, produce some small amount of light, or basically they would glow in the dark, right? So these fluorescent material. So similar type of material is used in as a scintillator, where your radiation is absorbed and some light energy or light rays they are produced. Uh, Now, I will explain you the working of it, although it's quite technical, but you do not need to go much into the detail. So this light um, rays, what it does is it propagates to the photocathode. And when this light ray is incident on this photocathode, electrons are produced. So mm, photocathode, it acts like your photo detector, or basically, for analogy, I could give you an example of solar panels. Yeah. So solar panels, what happens is when the light falls on the solar panel, some electrons are produced, right? Or basically, you could produce electricity. So similar type of thing is happening at the photocathode. So when the light which is being generated by this scintillator is hitting on this photocathode, some electrons is produced. Now, uh, as you might have observed, the fluorescent material, they do not produce quite a large amount of light, right? So it would just glow a little bit. You could see you could observe the light, but it's not sufficient enough. Right, so the electrons which are produced, they are also not very sufficient enough to be detected that easily. Right, so what they have, or this device have, is a photomultiplier tube. So this electrons, they are then incident onto this curved, these are anodes. Right, so these are anodes, but they are curved in disc shape, just to focus the electrons onto the next anode. Right, so these are again curved anodes. So what happens is this single electron, let's say, because of the light, only one electron is produced. Right, so this electron will get attracted towards the anode. And when it hits the anode, some secondary electrons are generated. Right, so this electron gets multiplied into two or multiple electrons, right? Because of the collision between the atoms of the anode and this electron, some additional electrons are produced, right? Then again, they are, sent, or they are attracted towards the second anode over here, curved anode. Again, because of that hitting, some additional electrons will be produced, right? So this process is repeated a couple of times, and finally you would be able to get sufficient number of electrons, basically sufficient enough to be detected or to produce a small amount of voltage, right? So that voltage, or that electricity, or the current is measured by this measuring device, and based upon the value of the current which is being produced, you could identify how your radiation is, or how intense your radiation is, right? So you could see in this animation that these electrons, they get multiplied as and when they collide with the curved anodes over here. And finally, you would get some voltage. So the magnitude of the voltage would depend upon the intensity of the radiation. So basically, this could be used for detecting um, either alpha, beta, or gamma rays, right? It could detect all three types of radiations, and it also gives the information about the intensity of radiation. The intensity or the energy of radiation. Okay. Now, I mentioned it could be, it, it is basically able to detect alpha, beta, and gamma radiation, but not all of them together. So alpha is detected by zinc sulfide. So if you replace this material over here, so currently it's sodium iodide and it is only able to detect gamma radiation, right? But if you replace it with zinc sulfide, it would then become sensitive to alpha, right? And if you replace it with anthracene, it could detect beta radiation. So along with these advantages, it is quite selective as well, right? Because only a particular material would be able to detect uh, particular radiation, right? So it is quite selective. So it can detect alpha, beta, and gamma radiation, and it is quite selective, right? So you could identify whether your radiation is either alpha, beta, or gamma. You could identify you would get the information about the energy of the radiation or the intensity of the radiation. You could, if you are using this scintillation counter. So overall, it basically solves all our problem. It could be made uh, quite smaller in size. It could be portable. So I think the digital detectors, so they have a pen kind of a structure. So they are quite small. They could be carried in your pocket, right? And it would display the numbers instead of waiting for a long time to get your photographic film developed. You could use a digital display scintillation counter, right? Um, but yes, you need to use a particular type of material in this case to detect alpha or beta or gamma. So if you want to detect other type of radiation, you would have to change this particular scintillation here. Right. So okay. Yeah, so this measuring background radiation, we have already seen this experiment. So basically in this experiment, usually in school or in labs, we use Geiger-Müller tube, where we have sufficient space and we do not have to carry our equipments everywhere, right? So if we do not need a portable device, this is the best way of measuring your background radiation. So you have your Geiger-Müller tube and you have your counter, right? And then you have a stopwatch. So you set the stopwatch and start your experiment of basically taking down the readings over a period of time, right? I will I will show you this experiment, or we'll try and deduce some calculation based on this experiment in the other classes as well. So basically I will share some experimental video, and from the video I've taken down the readings and we could plot some graph and we could calculate the half-life period and all, right? So we'll discuss about this type of setup in detail. But basically what we do is we set up the apparatus as shown below. So you have Geiger-Müller tube, counter, and a stopwatch, and you count the Geiger-Müller, you connect the Geiger-Müller tube to a counter or a rate meter and take a count for at least 1 minute, right? So you set the timer for 1 minute and you take the count after 1 minute. Then again, you take multiple readings for it, you record them and repeat or complete one count for a long period of time. So basically based on, if you know, like the time, so after 1 minute, 2 minutes, 3 minutes, you get some count. So 260, 340 or something like this counts you will get as a result of this experiment. Right. So based on these two readings, you could calculate the activity of the radioactive material. Right. And you could use this type of experiment for other calculations as well, which we will discuss in the next class. So today we are left with approximately, I think, 15 minutes or something, 17 minutes. So today I'm going to try something new. And what we'll do is I will use the Brightspace and split you up into smaller groups. And you can discuss amongst yourself. I'll give you 10 minutes for that. Right. So let me pause the recording.